You ever stare at a math question and just get that feeling that there's a secret code you're missing? Well, guess what? Today, we're becoming code breakers. We're going to tackle 3 classic problems that look super tricky on the surface, but are actually hiding some really simple, elegant logic. So let's get into it. So, what is that hidden trick? What's the secret sauce? Here's the deal. These problems aren't always about how much you can calculate. Nope. More often than not, they're straight-up logic puzzles. It's less about the number crunching and way more about what you can see. Okay, let's open our first case file. I like to call this one the composite imposter. We're looking at an expression that does its absolute best to look like anything but a composite number. But we're onto its game. And here is our suspect. At first glance, it just looks like a mess of multiplication and addition. Now, your first instinct might be to whip out a calculator and multiply it all out, but that's the trap. The question isn't asking for the final number. It's just asking why it's composite. So, how do we prove it without all the heavy lifting? Well, first, we've got to know the rules of the game. A composite number is basically any whole number that has more factors than just one and itself. Simple as that. So our mission is to find just one other factor. If we can do that, we've cracked the case. And the solution is a beautifully simple 3-step process. First, you just have to spot the common factor. See how the number 17 is in both parts of the expression? That's our big clue, right there in plain sight. Step 2, we pull that factor out. That leaves us with 17 multiplied by, well, some other number in parentheses. And honestly, it doesn't even matter what that other number is. We've just proven the entire expression is divisible by 17. Boom. Case closed. All right, one mystery down. Let's move on to our next puzzle, the quest for 0. This one is all about the power of numbers, and it asks a really specific question about what's possible and what's totally impossible. So here it is. Can the number 14, raised to the power of n, whatever n is, ever end with the digit 0? I mean, think about it. 14 squared, 14 cubed, 14 to the power of 1,000,000. Could any of those possibly end in a nice round 0? Let's investigate. Let's just lay out the evidence side by side. For any number to end in 0, it has to be divisible by 10. And for that to happen, its prime factors, its fundamental DNA, have to include both a 2 and a 5. Those are the magic ingredients. But when we look at the DNA of our number, 14, what do we find? A 2 and a 7. That crucial ingredient, the prime factor 5, is just missing. And here's the unbreakable law that locks this case shut. The fundamental theorem of arithmetic. This basically says that every number's prime factorization is totally unique, kind of like a fingerprint. You can't change it. So since 14 doesn't have a 5 in its DNA to begin with, raising it to any power in the universe is never going to magically make one appear. So the bottom line is this. No matter what you make, 1,000, a billion, whatever, that prime factor 5 will just never be part of the equation. And that means 14 to the power of n can absolutely, positively, never ever end in the digit 0. Mystery solved. Okay, for our final mystery, we're taking these ideas out of the abstract world of numbers and onto the racetrack. This is one of those classic word problems that shows just how often these logical tricks show up in disguise. So, meet Alice and Bob. They're on a circular track. They start at the same place, at the same time, but they're running at different speeds. Alice is a little faster. She does a lap in 24 minutes. Bob takes a bit longer, at 32 minutes. The big question is, when are they going to be back at that starting line at the exact same moment? To solve this little puzzle, we're going to do something that should feel pretty familiar by now. We look at the prime factor DNA of our key numbers. The number 24 breaks down into 2 cubed times 3, and 32, that's just 2 to the power of 5. This is our first step to finding that exact moment when their paths sync up perfectly. So, what are we actually looking for here? We're on the hunt for something called the least common multiple, or the LCM. Now, I know that sounds all formal and mathy, but it's just a fancy term for the very first number that's a multiple of both Alice's time and Bob's time. This whole big word problem, it's just an LCM puzzle wearing a tracksuit. So how do we find it? We just take the highest power of each prime factor we see in their DNA. In this case, that's 2 to the power of 5 from Bob's time and the 3 from Alice's time. We multiply those together. 32 times 3, and we get 96. That's it. They will meet again at the starting line in exactly 96 minutes. So, after cracking all 3 of these cases, what have we actually learned? Well, we've put together a pretty powerful logical toolkit, one that you can use to tackle problems that seem way more complicated than they really are. Let's recap our master keys. First, always look for those common factors hiding in plain sight. Don't just jump straight to calculating. Second, remember that every number has a unique prime DNA, and that DNA dictates what it can and can't do. And third, get good at recognizing when a tricky word problem is just a familiar concept, like the LCM, wearing a clever disguise. And that leaves us with one final thought to chew on. The next time you're faced with a tough-looking question, just stop and ask yourself, is this really about complex calculations, or is it just a simple logic puzzle waiting for me to solve it? You might be pretty surprised by the answer.